Hello, everyone. We're going to be doing our last section, section 11.5, which is on partial fraction decomposition. So we have four objectives. Objective 1, we want to decompose P over Q, where Q has only non-repeated linear factors. Objective 2, decompose P over Q, where Q has a repeated linear factors. 3, decompose P over Q, where Q has non-repeated irreducible quadratic factor. And 4, decompose P over Q, where Q has a repeated irreducible quadratic factor. So all right, let's get started. So first things first, let's go ahead and just consider adding rational expressions that look like 3 over x plus 4 and 2 over x minus 3. If we want to find the sum, what we would end up doing is that we would multiply each one of the functions by the other's denominator. So we would multiply 3 over x plus 4 times x minus 3 over x minus 3, so that we can end up with the same denominator in both terms. Then 2 over x minus 3 would be multiplied by x plus 4 over x plus 4. Then we would get that both terms would have the same denominator, and then you could go ahead and add them. When you do, that would look something like 3 times x minus 3 plus 2 times x minus 4 all over x plus 4 times x minus 3. And when we add that, we would end up getting 5x minus 1 divided by x squared plus x minus 12. So if we want to go in reverse, so if we want to start with 5x minus 1 divided by x squared plus x minus 12, we want to get back to 3 over x plus 4 and 2 over x minus 3, doing that procedure is going to be called the partial fraction decomposition. And the two simpler fractions are going to be called the partial fractions. So 3 over x plus 4 and 2 over x minus 3 would be your partial fractions. Now recall that a rational expression is the ratio of two polynomials, say p and q, when q is not equal to 0. So you can express things like 3 over x plus 4, 2 over x minus 3, or 5x minus 1 over x squared plus x minus 12. You can rewrite those as p over q, where q just has to not be equal to 0. Then recall that a rational expression p over q is rational if the degree of p is less than the degree of q. So degree means degree of the variable. So in this case, for 5x minus 1 over x squared plus x minus 2, the degree of 5x minus 1 is 1 because we have x to the first degree. And then x squared plus x minus 12 has a degree of 2 since x is squared, or x has the second degree. Otherwise, it's improper. If we see that p has a greater degree than q, it would be an improper expression. Then the partial fraction decomposition of p over q is going to depend on the factors of q, and q can only contain factors of the following type. It can only contain linear factors. These are factors of the form x minus a, where a is a real number, or irreducible quadratic factors. These are going to be of the form ax squared plus bx plus c, where a, b, c are real numbers. A is not equal to 0, and b squared minus 4ac is going to be less than 0. When it's less than 0, this makes sure that the negative discriminant guarantees that ax squared plus bx plus c cannot be written as the product of two linear factors with real coefficients. In other words, if we were to use the quadratic formula, where we know we have b plus or minus the square root of b squared minus 4ac divided by 2a, then we do see that b squared minus 4ac, which is under the radical, that value has to be positive to even be able to factor a quadratic function. But if it's negative, then that means that it is irreducible. There's no way that we can factor that function out. So all that's saying is that you ensure that b squared minus 4ac is less than 0, so you make sure that it's negative to ensure that your function is going to be irreducible. So it turns out there are going to be 4 cases of this to be examined, hence our 4 objectives. So objective 1, we want to decompose p over q, where q has only non-repeated linear factors. So remember, our linear factors look like x minus a, where a is not equal to Nope, we're just a is a real number. So a can be equal to 0. In this case, it just has to also be a real number. So the details of case 1, where q only has non-repeated linear factors. This means that under the assumption that q has only non-repeated linear factors, the polynomial q will have the form q of x is equal to x minus a sub 1 times x minus a sub 2, so on, until you get to x minus a sub n. So this can look anything like x minus 2, x minus 3, x minus 4, anything along those lines, where no two of the numbers a1, a2 to an are going to be equal. In this case, the partial fraction decomposition of p over q is then going to be of the form p of x over q of x is equal to capital A1 divided by x minus lowercase a1 plus capital A2 divided by x minus lowercase a2, and so on until you get to a capital A sub n divided by x minus lowercase a sub n, where the numbers capital A sub 1, A sub 2, A sub n are then to be determined. And that's what the main point of our problems are going to be, is to solve for those capital A sub 1s, A sub 2s, A sub 3s, so on. All right. Also, just a side note, because you want your answer in the form of x minus a1, x minus a2, a just has to be a real number. So that also means that you can have x plus 1, x plus 2, x plus 3, anything along those lines as well. All right, so let's go ahead and do example 1. We want to find the partial fraction decomposition of x divided by x squared minus 5x plus 6. First things first, first thing you always want to do is you want to factor the denominator, or try and find out it's irreducible. So first, factor the denominator. Our denominator is x squared minus 5x plus 6. So we want to find values that multiply to 6 and add to negative 5. And those values would be x minus 2 and x minus 3. So this also tells us that the denominator contains non-repeated linear factors. It just means that we don't have x minus 2 times x minus 2. We see that x minus 2 and x minus 3 are both very distinct factors in their own, because a sub 1 and a sub 2, they're not equal to each other. Now we want to decompose the fraction according to equation 1. So now we decompose the fraction according to equation 1. So our fraction, which was x divided by x squared minus 5x plus 6, we are going to end up decomposing this into a divided by x minus 2 plus, and instead of writing a sub 1, a sub 2, a sub 3, I find it quite confusing. We're just going to write a plus b. So our fraction is going to decompose into a divided by x minus 2 plus b divided by x minus 3. And now our job is to solve for a and b. So we can say we want to solve for a and b. All right, so to find a and b, we can clear the fractions by multiplying both sides by x minus 2 times x minus 3. Which we know that this is also equal to x squared minus 5x plus 6. So essentially what this is going to do is that it's going to cancel out our x squared minus 5x plus 6 from our original fraction. So we'll just be left with x. And then we can multiply a and b by the corresponding other factor. So this gives us x is equal to a times x minus 3 plus b times x minus 2. Because essentially when we multiplied a over x minus 2 by x minus 2 times x minus 3, our x minus 2's canceled out. What you were left with was a times x minus 3, and then the same thing for b. When you had b over x minus 3, when you multiplied by x minus 3 times x minus 2, your x minus 3's canceled out, so you're just left with b times x minus 2. And then since x minus 2 times x minus 3 was equal to x squared minus 5x plus 6, the whole denominator was canceled out for x divided by x squared minus 5x plus 6, which just left us with our numerator of x. So we have x is equal to a times x minus 3 plus b times x minus 2. So let's go ahead and expand. We'll distribute our a and our b into our factors. This gives us ax minus 3a plus bx minus 2b. And now we can go ahead and group our variables together. So we're going to group our x terms. So we have x is equal to a plus b times x. And then we'll have our constants. Then we'll have plus negative 3a minus 2b. So what we have now is that this equation is an identity in x. So we can equate the coefficients of like powers of x to get this. And I'm actually going to move these lines down one. So you're using this identity and you're going to have this set now of equalities. And we're going to say that 1 is equal to a plus b and 0 is equal to negative 3a minus 2b. And we state that a plus b is equal to 1. This is because a plus b times x has to be equal to 1x, which means that if they're equal, a plus b has to be equal to 1. Same thing with negative 3a minus 2b. They have to be equal to 0 since there are no constants in p. P is our numerator. When we think of our fraction that we're taking the partial fraction decomposition of, we think of this as p over q. So in this case, p is just x. So there's no constants in our original numerator, which means that negative 3a minus 2b has to be equal to 0. So before, when we wrote this, this is technically x plus 0. So what we're stating here is that x has to be equal to a plus b times x, and plus 0, bad color, let's write this like that, plus 0 has to be equal to plus negative 3a minus 2b. So we're going to say that these have to be equal and these have to be equal. They have to be equal because that would be the only way that this expression would make sense. So we're stating that a plus b has to be equal to 1 so that we can get 1x, and that negative 3a minus 2b has to be equal to 0 so we can get that plus 0. That is the only way that we can make this statement true. So now we've established equations here. So we can use one of these equations to find a relation between A and B. The easiest one is that A plus B is equal to 1. If A plus B is equal to 1, this means that we can state A is equal to 1 minus B. So that's the easiest way. We state A is equal to 1 minus B. Let's just highlight that for now. So that anytime we see A, we can replace A with 1 minus B to have an equation in terms of only B. Our only other equation in this case is going to end up being 0 is equal to negative 3a minus 2b. We could plug it back into the same equation, but it's better to use the other one. So we have that a is equal to 1 minus b, then we'll plug into a equals 1 minus b into 0 is equal to negative 3a minus 2b to find the value of b. So we have negative 3a minus 2b. So this is going to be negative 3 times 1 minus b minus 2b is equal to 0. We can expand this out. This gives us negative 3 plus 3b minus 2b is equal to 0. 3b minus 2b is just going to be b, so we get negative 3 plus b is equal to 0, where we just add 3 to both sides to get that b is equal to 3. So then, if b is equal to 3, then a, which is equal to 1 minus b, is 1 minus 3, so we get negative 2. So we have b is equal to 3 and a is equal to negative 2. All of this said now, we found the values of a and b, but remember our final step in our partial fraction decomposition is rewriting this. So our final answer is going to look like thus. Our partial fraction decomposition is, and we state our original, which was x over x squared minus 5x plus 6. And remember, we said that this is equal to a over x minus 2 plus b over x minus 3. So a was negative 2, so we have negative 2 over x minus 2 plus b, which was 3 over x minus 3. And this would be our final answer. A final note before we are officially done with this problem is that if you want to check your answer, we can check by simply adding our partial fraction normally. So for the sake of time, we're not actually going to go through this, but I will show you how it works out and the check momentarily. So you can go ahead, look at the answer, pause it, make sure that you know what happened there, and then we'll move on. So there we have it. Here's our check. This is how we would go ahead and just check our answer. You would just add your partial fractions any other way that you would normally and just make sure that you get that answer from before. So if you really want to look over this check, I would highly recommend pausing the video and just looking over and making sure that you know how you got this answer. So, all right. Sometimes we can actually find A and B easier. We can also clear fractions like this. So if we have x is equal to what we had before, which was a times x minus 3 plus b times x minus 2, when we let x equal 2 in the expression, we see that the b term is equal to 0, and all that we're left with in this case is 2 is equal to a times negative 1, which then gives us a is equal to negative 2. So an easier way to clear out your fractions would be once you get to this point, you find whatever value of x would make one of those factors 0, and then you fill it in for x in every other place. So then you're essentially canceling out one of your terms because you've made it into 0, and you can solve for your other term and then do the same thing for the other term. So you'd be doing the same thing twice in essence. But it is faster to do it that way if you're able to. So then you do the same thing when you let x equal 3. That leaves you with b is equal to 3. Then we get the same answer as before with a is equal to negative 2 and b is equal to 3. So that's going to end up being a quicker way to clear out your fractions and the way that we will use from now on.